Hello everyone. So today I'm going to be showing you how we can calibrate images using step wedges within our TotalLab GxP 21 CFR compliant software. Hello everyone. So today I'm going to be showing you how we can calibrate our images within our TotalLab GxP module. Now, image calibration is reserved for our 21 CFR compliant pieces of software, which are all governed by the TotalLab GxP module. So it's part of the TotalLab GxP module. The reason being that the vast majority of our users that wanted to use calibrated images were already working in regulated sectors anyway, so it made more sense to just include that with the GxP module with the regulatory side of our software. So if I just log in here, I'll explain to you why you would want to work with calibrated images and why that offers the user a benefit. Now, obviously, one of the selling points of TotalLab software is that it's device agnostic. So if you had a lab with lots of different scanners or gel dock devices, you could use TotalLab software to analyze all of the data from all of those different manufacturers' devices, rather than having to use the software that comes with each device or the manufacturer's software for each device and then try and cobble together the data afterwards. So it means less training for the user and less time taken for analysis. As part of that unification of your lab environment, the ability to work with calibrated images allows users in different labs or within the same lab on different pieces of equipment to make sure that the data that they're reading from the image is all standardized. And you'll see as I move through this how that works by using step wedges and things like that and converting everything to kind of a fixed calibration point. So the first thing we have to do is to create a project with our step wedge in it. So your step wedge is basically something that you would scan on your scanner, your densitometer, or your gel dock device, and it has sections that are of a known optical density. So you'll receive manufacturer's instructions with your step wedge that will tell you what the optical density of each step is. So if I just come here and create a project here, I'll just call it step wedge. And I will bring in a step wedge here that I've got and then create it as a project. And I will check out the project. Now, I'm just going to calibrate it using the Phoretix 1D module, but I could, as you can see, I've got the different kind of modules plugged into my TotalLab GxP module. I could use any of these calibrate options because they're all connected to the same calibration module. So if I just click calibrate here, you can see that this is my step wedge. Now, when you first see it, it's being given a false colorway. So I can turn that off using the tick box here at the bottom. And the reason we present it in using a false color map, like a heat map, is because as you can see, as you get to the top, about above this kind of towards the top of the step wedge, it becomes very difficult to see where one step ends and the next begins. However, if we use the false color kind of heat map, but it increases the contrast of the different steps between the different steps and it will allow us to calibrate very accurately our step wedge. Whereas if I tried to do it here, I might not have my points as accurate as they possibly could be. So this makes things a lot easier and makes it a lot more accurate to be able to calibrate your step wedge. So I've got the image of my step wedge here. And if you click on the drop down arrow here, and if you go and edit calibration maps, you can create a new calibration map. So the calibration map is what's going to contain all of your data about what the optical density is for this step wedge at every step. So it will be built from the information you've got from the manufacturer. So if I create a new one, you'll see that I get one map 10 added at the bottom. If I click on the pencil, I can edit this calibration map. And here is where you would put in the optical density and the number of steps for your map, which would be part of the information, the documentation that you got from the manufacturer. So I know this step wedge has 21 steps, so I'll just pop 21 on, but I won't bother assigning them optical density. So if I apply the changes there, And then if I close down this window and I select from my drop down map 10. Now I could have given this, as you can see, I've got a few with different names on. I could have given this a custom name but didn't. So now I've got map 10 selected. What I can do is I can left click here on the first step of my step wedge and then drag my mouse down whilst still holding down my left mouse and release here. And as you can see, what the software does is it automatically evenly spaces out points where the image, the intensity of the pixels at the point here is going to be converted to the value that I inputted in my calibration map. Now you can have manual control over where you want these kind of sampling points to be. You just left click and drag them if they're not, if the evenly spaced kind of automatic mode of assigning calibration doesn't work out. And as you can see, it's not worked out here because not all of these steps are of exactly the same size. However, it's nothing to be worried about because we can just manually adjust them. But as you can see, as I'm manually adjusting these steps, this is the data. So these yellow squares here relate to the samples that are taken from all of these sampling points at every point. And this green line here is the line of best fit. It's basically the standard curve of what those pixel intensities are going to be when represented as optical density. So optical density is the reference, the normalization that will be applied by using a step wedge that will be applied to your image so that your images will be comparable regardless of what scanner, what scanning device, what lab they were scanned in. You can be sure that the intensities that you're looking at in your encoded within your image, are going to all be normalized to the same value. The benefit of which means if you've got a lab in Shanghai and they're scanning documents and you want to analyze them in Amsterdam, or you want to send them somewhere else to America, you can, if you've got 3 or 4 labs all across the world, all using different equipment, you can still be sure that when one analyzes an experiment, their results are going to be comparable to the results that were analyzed somewhere else because they're all working off the same reference values. A pixel value of 10 is always going to be an optical density of 0.5, for example, regardless of what it's been scanned on or where it's been scanned. So that's the benefit of calibrating your equipment and using calibrated images. So as you can see, this is the line of best fit, and we've got a number of different lines, different calculation methods that we can use mathematically to work out what our line of best fit is. Because obviously, if you have a pixel value between your 2 sampling points, it has to be extrapolated from the information that the program's been given. So the line of best fit and how your step wedge should be calibrated and used and set up will be included in the information that you get from the manufacturer from whom you've bought your step wedge. So these are the options we have within our calibration section of our TotalLab GxP module. We've got the option for quadratic, linear, cubic spline, log linear, log quadratic, and first order Lagrange lines of best fit. And we've also got the option to choose the best. Now, this option should only be used if you don't know what is the correct, the manufacturer recommended kind of standard curve option that you should be using. And if you click that button, the software will basically check all of the different mathematical models for creating your line of best fit, and we'll choose the one with an R² value closest to 1. So what that means is it will choose the line that best fits, most accurately or most closely fits the extrapolated sample data that you've given it. So essentially the line that most closely resembles this curve that you've got here in your sample data. We've also got the option to intersect the origin here. which means that at a pixel intensity of 0, you also have an optical density of 0. However, if any of your sample points, if you don't have a sample point that reaches pixel intensity of 0, that really shouldn't be represented as an optical density of 0 because that's almost a false result. It's very rare to actually have pure 0, pure white pixel intensity or pure black pixel intensity, depending on which way your image is. And you can also represent all of your extrapolation points as a table. So you can see that here step 0 has a pixel intensity of 13, 14, 15, 16, 16, and that's because these points 4 and 5 are actually in the same step wedge. If I drag that across, should change. So those are all the options we've got surrounding calibration. We've also got the option to undo and redo, of course. So those are all of the options that we've got for setting up our calibration map. So this is now, this calibration map, map number 10, is now calibrated, converting the pixel intensities from those different steps in the step wedge into a value which is now optical density. So if I close this down now, it will ask me if I want to save my calibration file. I'll select yes. So what we need to do now is we need to check the project back in, click OK. And when the project is checked back in, we now get the option to export the calibration. So if we click on export calibration, it now gives us the option to export the calibration that we've performed here as a file. Now the benefit of it being a file that exists kind of separate to the software is that this file can be transmitted to other people. So if you wanted to send someone the calibration file that you've been using, so if you've calibrated one of your scanners and you want to send someone else the calibration file because it's their time to use the scanner and they want to calibrate the software exactly as you have, you can just email them this file and then they can load this file and the calibration's already been done for them. They don't need to redo it. You can also, of course, apply the calibration yourself multiple times. So if you have multiple different images that you want to calibrate, you can use the same calibration map for each one, or you can use different calibration maps for each different image. So if you've got 3 different scanners and you're analyzing 3 different images, but it's all within the same piece of software, you don't need to go out and recalibrate them all. If you've already calibrated those scanners, you would just apply the calibration maps that you've already defined from those 3 scanners in that example. So if I just call this demo calib, save. So now if I want to calibrate an image and apply that calibration that I've just created to an image, so convert the pixel values of that image into a value that's represented by optical density, this is how I would do it. So I create a new project again. I call this calibration demo, and I'll just drop a random, grab this image here. So I'll just create a project, calibration demo. So if I have a look, click on calibration, no. If I check this project out and I inspect it, you can see that I get, so this is the image that I'm looking at, these are the pixel values. You can see that the calibration is represented as it's being not calibrated. So this image is not calibrated. As I hover over it, you can see that the pixels just have a pixel value. If I opened it in Phoretix 1D, as I hover over it, if I just invert the measurements here, as I hover over the sections of the image, you can see that, if I just turn on one of the channels, you'll be able to see that on the lower left hand corner, the pixel intensity is represented as just a number. It's not optical density. So if I wanted to calibrate this image, what I would do is I would click on apply calibration. As we can see, the image is uncalibrated at the moment, and I would browse to the calibration file that I've just created, and I can view it from here as well, and it will show me which calibration file I'm looking at, it will show me an image of the step wedge and the way the calibration is set up. So if you are using multiple step wedges for multiple images with multiple scanners, you'll be able to check before you apply the file. You won't have to just rely on the file name. So I can say, yep, I want to apply this 21 step wedge with map 10 on it. That's the calibration file that I want to apply to this image. Click on Calibrate, we'll say Calibrated yes, and then we can re-inspect the image. And now we've got the step wedge, so it says, I've got map 10, I've got my calibration map 10, my unit is optical density for this particular map, these are the steps that I've calibrated. And now you can see that when I hover my mouse over somewhere, it will give me the pixel value, the pixel intensity value, and also the calibrated value in optical density. Close that down, and then if I reopen my Phoretix 1D analysis software, and if I just have my one channel on, you can see that in the lower left hand corner now I get optical density rather than the pixel value, the pixel intensity value as I was getting before. So that's how we handle image calibration in Phoretix 1D or TotalLab GxP, however you want to see it. So the same process would be applied to using SaneSpots, SpotMap, any of our image analysis software. The process is the same. So if I wanted to do a 2D image, it would be exactly the same, defining the step wedge, creating the calibration file, and then applying that calibration file to all of the different images that I wanted to calibrate. As ever, thanks for watching, and if you'd be interested in ImageLab's image analysis software or our 21 CFR compliance software, please check out the links in the description below.